Okay, I hope you guys are doing well today. Um, Sorry about that. Goodness gracious, and my antivirus is being dumb as well. Okay, sorry about that. Does anybody have any questions regarding any homeworks, assignments, or anything like that before we start with today's lecture?
Yes, I have one from yesterday's ICA.
Okay,
It's finding Thevenin. I keep getting 26.02 when I'm supposed to be getting 27. So the first problem.
so let me pull that guy up. So that would be ICA number 10, right?
Correct.
And you said the second problem, this guy?
The first one.
First problem.
I keep getting, for Thevenin at least, I get 26.0217.
Okay,
But
so
yeah.
So we'll take a look at this guy really quickly, and that'll kind of serve as a review for what we're about to do today anyway, since we're just going to be looking at Thevenin and Norton equivalent circuits again. But this time we're going to include what happens when dependent sources are around. So if we're specifically trying to find the Thevenin voltage in this system, that is going to be the voltage present across the open circuited terminals, which would be this voltage right here. Now, one thing that we can do is we can observe that there is no current whatsoever flowing to the right through this 160 ohm resistor because it's not part of a closed current carrying loop. Since there's no current flowing through that resistor, there's no voltage drop across this resistor either, so we can effectively treat it as if it weren't there, which means that our Thevenin voltage is really just the voltage drop across this current source. Okay, so I'm going to choose to use nodal analysis to determine this particular voltage. Okay, so I'm going to just identify my nodes real quick. Let me do this guy right here, this guy right here, this guy right here, and then we'll do green on bottom. And I'm going to choose that bottom node as my ground node. So this will be our voltage VA, this will be VB, and this will be VC. And VC is going to be the same thing as our Thevenin voltage that we're interested in. Just to make sure you guys understand that, the positive polarity terminal of VTH is at node C, and the negative polarity terminal is here at ground. So VTH is equal to VC minus 0, or just VC. So we have a supernode here around this 1.2 volt source. So our supernode is going to give us a voltage relationship equation that is simply VA is equal to 1.2 volts. Because this supernode contains ground, we will not write a KCL equation for this supernode. And so now we're on to the next step where we just write our KCL equation at all remaining non-reference nodes, which in this case would be node B and node C. So when we apply KCL at node B, we'll get VB minus VA over 49 ohms plus VB over 180 ohms plus VB minus VC over 96 ohms is equal to 0. And when we apply KCL at node C, we'll have VC minus VB over 96 ohms minus 0.2 amps is equal to 0 because I've already noticed that the current flowing to the right is 0 amps, so it's not adding anything to add 0 to these equations. So solving this system for VA, VB, and VC, I'll need to throw that into my calculator real quick. So I'm lazy and I'm just going to set this up as a 3 by 3 system. In my first equation, my coefficient for VA is 1, my coefficient for VB is 0, my coefficient for VC is 0, and my constant term is 1.2. In my second equation, my coefficient for VA is negative 1 over 49. My coefficient for VB is positive 1 over 49, plus 1 over 180, plus 1 over 96. And my coefficient for VC is negative 1 over 96. My constant term is 0. In my third equation, my coefficient for VA is 0. My coefficient for VB is a negative 1 over 96. And my coefficient for VC is positive 1 over 96. And my constant term will be positive 0.2 when I move it over to the other side. Solving this, I get VA is 6/5 of a volt, which is the same thing as 1.2. VB is 1980 over 229 volts. And VC comes out to be 27.846288. So I'm just going to leave that as 27.846 volts, which does agree with the answer. So I think that was Joseph. Was that solution helpful?
Yeah, I did all the steps. It's just I keep getting 26 instead of 27, but I'm going to try it again.
Yeah, it may just be putting something into your calculator in slightly wrong, because if your equations match mine, then you should be getting the same results as me. So I genuinely don't know unless I can physically see what you put in your calculator.
Yeah. All right. Thank you.
No problem. Any other questions about anything before we move on to the lecture? Alrighty. So today is going to be Thevenin and Norton equivalent circuits 2. And this is just, the same thing that we did on Wednesday, except now we're going to include dependent sources. So I've got a random circuit analysis textbook here, and I'm just picking a problem for us to look at. So let's look at this guy where we're going to have a voltage controlled current source here. So this is going to be 0.5 Vx. Here we're going to have a 2 amp current source. Across here we'll have a 4 ohm resistor, where Vx is defined as the voltage drop across this 4 ohm resistor with positive polarity terminal on the left. Here we have a 2 ohm resistor. This is going to be a 3 volt source. This is going to be a 6 ohm resistor. This will be terminal B. This will be terminal A. And our ultimate goal here is to find VTH, I Norton, and RTH for the circuit. And let's say that we're going to have plus on top, and our reference direction is down for I Norton. So we'll find VTH first. Okay. So essentially, just like we did in class on Wednesday, When we're finding VTH, we're simply finding the voltage drop across our open circuited set of terminals, and we're told explicitly to put the positive polarity terminal on top. So I'm going to redraw my circuit here. And our Thevenin voltage is just going to be the voltage drop across this 6 ohm resistor. So realistically, if we were going to do nodal analysis here, I see 1, 2, 3 nodes plus a reference node. And if we're going to do mesh analysis, it's going to be 3 meshes. However, we have 2 current sources on the perimeter of the circuit. So really, we're just going to have 2 current relationship equations to deal with, and then 1 KVL loop. So I would actually probably do mesh here. So let's call this guy mesh current I1. This will be mesh current I2. And this will be mesh current I3. Let's see. Our controlling variable relationship is going to be Vx is equal to 4 ohms times I1 minus I2. Just to remind you guys, it's I1 minus I2 because I1 is flowing into the positive polarity of terminal of Vx, and I2 is flowing into the negative polarity terminal. Then I'm going to have my current relationship equations. So that's going to look like 0.5 Vx is equal to I1. Then I'll have 2 amps is equal to I2. And then lastly, I'll write a KVL equation around mesh 3. So that's going to look like negative 3 volts plus 2 ohms times I3 minus I1 plus 6 ohms times I3 is equal to 0. And now I'm going to solve this system. Let's see here. So I'm going to substitute in I2 is equal to 2 amps into this guy right here. And so my system of equations, my variables are going to be I1, I3, and Vx. So let's see. So in my first equation, which is my Vx equation I have written at the top, my coefficient for I1 is going to be positive 4. My coefficient for I3 is going to be 0. And my coefficient for Vx is going to be negative 1 when I move that over to the right-hand side of the equal sign. My constant term is going to be 4 ohms times 2 amps is 8 volts when I move that over to the left-hand side of the equal sign. In my second equation, my coefficient for I1 is 1, my coefficient for I3 is 0, and my coefficient for Vx is 0.5, and my constant term is 0. And in my third equation, which is the bottom one, my coefficient for I1 is negative 2. My coefficient for I3 is positive 2 plus 6. My coefficient for Vx is 0, and my constant term is positive 3. So when I solved this guy, I got I1 is equal to 4/3 of an amp. I3 is equal to 17/24 of an amp. And Vx is equal to -8/3 of a volt. So before we move on from here, did anyone else get similar results if you followed along with your equation solver? Thank you for the thumbs up, Trevor. So now that we know what those three mesh currents are, as well as the voltage Vx, how can we use that information to find our Thevenin voltage? Does anybody have any thoughts? So our Thevenin voltage is defined as the voltage drop across the 6 ohm resistor. So I think that VTH is just going to be 6 ohms times whatever mesh current is flowing through the 6 ohm resistor. So which mesh current is flowing through the 6 ohm resistor?
I3.
I3. So I'm just going to directly substitute in here 17/24. And I'm not going to try to do that in my head. So 6 times 17/24. I get, oh, well, I guess I could have done that. 17/4 of a volt. So before we move on to finding our Norton current, does anybody have any questions about the analysis that we did there? All right. So to find our Norton current, we're going to start with our original circuit. So 0.5 Vx, 2 amps, and what we're going to do is we are going to short circuit those terminals. And we're told in the problem statement that the reference direction for our Norton current was down. So I think I'm going to wind up doing mesh analysis again here because I'm only going to have 3 meshes, but I'll have, let's see, 1, 2, 3, 4 nodes, including ground, and then also that controlling variable relationship. So realistically, nodal or mesh could work here, but I think finding I Norton using mesh will be a little bit easier because we're looking for a current. So this will be our mesh current I1, I2, and similar to what I did towards the end of class on Wednesday, I'm going to call this guy our mesh current I3, where I am effectively bypassing the 6 ohm resistor because it is directly in parallel with that short circuit that we're measuring the Norton current through. And whenever our resistor is in parallel with a short circuit, we know that the voltage drop across it is going to be 0 because the voltage drop across a short circuit is always 0. And because the voltage drop across the resistor is 0, that means there's no current flowing through it either. So the 6 ohm resistor can just be neglected. So the mesh analysis that we're about to do is going to look pretty darn similar to the equations that we just wrote when we were finding VTH. Starting with my controlling variable relationship, we're going to have Vx is equal to 4 ohms times I1 minus I2. Our current relationship equations are going to be half of Vx is equal to I1 and 2 amps is equal to I2. And our KVL equation around mesh 3 is going to look like negative 3 volts plus 2 ohms I3 minus I1 is equal to 0. So I'm going to solve that in my system solver. The only thing that I need to actually change, so my first equation is going to be exactly the same because I'm just substituting in that 2 amps again for I2. My second equation is completely unchanged. My third equation, my coefficient for I3 is now just going to be plus 2. And then everything else is the same. So when I solve it, I got I1 is once again 4/3 of an amp. I3 this time is 17/6 of an amp. And Vx came out to be once again negative 8/3 of a volt. From here, our Norton current is going to be what? So how is our Norton current related to our mesh currents?
It's just I3.
Exactly right. Thank you. So it's just I3. So that'll be 17/6 of an amp. And so for finding RTH, we could simply say that our Thevenin resistance is the ratio of our Thevenin voltage to our Norton current. So that's going to look like 17/4 divided by 17/6. And I can write this as 17/4 times 6/17 per amp. The 17s cancel each other out, and I wind up with 6/4 or 3/2 volts per amp, which is an ohm. So that's what I got for the Thevenin resistance. Okay. So before we kind of expand on this, does anybody have any questions about what we did solving for I Norton, or how I used the Thevenin voltage and the Norton current in order to determine RTH? All right. So what if we wanted to find the Thevenin resistance of this circuit directly? Okay. So when we were looking at problems on Wednesday, there were no dependent sources, and so we just had resistor combination problems. With these dependent sources in, that's going to be messed up a little bit, okay? So I'm going to draw our original circuit again, and we're going to explore other ways that we could to find RTH, okay? So here's my dependent source. I'm drawing my 2 amp source here for now, but I'll wind up turning it off in a moment because we find the Thevenin resistance by looking at a dead network that was mentioned in class on Wednesday. So we're finding the Thevenin resistance looking in to these terminals. And as I mentioned a moment ago, we need to be looking at a dead network, which means this 2 amp source is going to be turned off. So I'm replacing it with an open circuit. And this 3-volt source is going to be turned off. So I'm replacing it with a short circuit. We can only turn off independent sources. So any dependent sources we have will always be on, okay? So that's why that 0.5 VX dependent source is there, because I literally cannot turn it off. So we now have this kind of awkward network that we're trying to find the Thevenin resistance of. We know ultimately that we should expect to get an answer that is 3/2, but just by looking at this guy, it would be very hard for us, if not impossible for us, to figure that out, right? So what we're going to do is we're going to rely on Ohm's law, but a little bit differently. So this is something that we've at least acknowledged before, but I don't know if it's something that we've explicitly used. So if we think back to our third class meeting, when we introduced the concept of Ohm's law, and for what it's worth, don't write this down. I'm going to wind up erasing it here in a moment anyway. We said that if we had a linear network where we didn't really know or care what was inside of it, but it was a 2-terminal network like so, and we excited this network with some sort of DC source, doesn't matter if it's a voltage source or a current source. If we measured the voltage drop across the terminals, so I'm going to call this V test, and we measured the current flowing into the terminals, I'm going to call this I test, then the resistance of the network was simply the ratio of V test over I test. Well, what we have is essentially that black box network. And so what we can do is we can choose to excite the network, measure the voltage across the terminals of the network and the current flowing into the terminals of the network, and then use those 2 pieces of information to determine the Thevenin resistance. Okay. So this is just Ohm's law, but it's from a kind of experimental perspective as opposed to just, V is equal to IR, although ultimately that's what it's going to boil down to at the end. So let me erase this recap thing here. And so what I'm going to show you guys now is what's commonly referred to as the test source method for determining the Thevenin resistance of a network. You can absolutely use this method if there aren't dependent sources, but it's usually easier to just do resistor combination techniques. Okay. So across the terminals of this network, I'm going to apply a source. Okay. And we'll decide what that source is in just a moment. But what I'm interested in is this voltage, V test, and this current, I test. Okay. Now, it literally does not matter if we choose to use a test current source or a test voltage source. So I'm actually going to work it both ways to show you that we're going to get the exact same result. Okay. Uh, let's start with a test voltage source. So I'm arbitrarily choosing positive polarity terminal for the voltage source on top, negative polarity on bottom, but it literally does not matter. Okay. You could choose either polarity, and I'm going to choose 1 volt here as the value of my test voltage source, but this also does not matter. Okay. So if you wanted to use 5 volts, if you wanted to use 17.4 volts, whatever you feel like is perfectly acceptable, you're going to get the correct result 100% of the time, regardless of what you choose for V-test, because we're dealing with a linear network. Okay. So if I choose to use a test voltage source, then V test is a known quantity. And really, the only thing I'm actually then interested in is the current I test. So let's solve for that current I test, in this case, using mesh analysis. Okay. So this will be mesh 1. Here's mesh 2. And here's mesh 3. I'm going to ask you guys a question here. I'd like for somebody to at least attempt to answer it. But why aren't I labeling a mesh current in the bottom left-hand corner?
It's open, so it doesn't complete the loop.
Exactly right. So there is no mesh current in that bottom left-hand corner because there's no completed path for the current to flow through. So we know inherently that if we put a mesh current down here, I'm going to erase it in a second, but if we put one down here, let's call it I4, this guy has to be 0 because there's an open circuit in this path, okay? So that's a mistake that I commonly see students make, is including meshes or mesh currents for meshes that contain an open circuit. It's pointless. That current has to be 0. All right. So thank you for that, Joseph. Okay, so let's look at our circuit analysis here. So our controlling variable here, Vx, is just going to be 4 ohms times I1. And we also know that I1 is equal to 0.5 Vx. Okay. We'll wind up rearranging one of these guys here in a moment because those guys have very similar information, so we can just come up with one equation from them. But before we do that, our KVL equation around mesh 2 is going to look like, let's see, 2 ohms times I2 minus I1 plus 6 ohms times I2 minus I3 is equal to 0. And then our KVL equation around mesh 3 is going to be 6 ohms times I3 minus I2 plus 1 volt is equal to 0. So I'm going to play around with this guy just real quick. So we have I1 is equal to 0.5 Vx. So that would be I1 is equal to 2 I1 because 4 I1 times a half is 2 I1. And so if we have I1 is equal to 2 I1, that essentially just means that I1 has to be 0 amps. Does anybody have a problem with that? Okay. Okay. So if we know that I1 is 0, then we're really just solving for I2 and I3. So I'm just going to solve this system. So my first equation is going to be for I1. So I'm going to have 1 I1 plus 0 I2 plus 0 I3 is equal to 0 amps. My second equation, I'm going to have negative 2 times I1 plus 8 times I2 minus 6 times I3 is equal to 0. And in my third equation, I'm going to have 0 I1, negative 6 I2, positive 6 I3 is equal to 1 volt, no, excuse me, negative 1 volt. When I move that 1 over to the other side of the equal sign. And I wound up getting I1 is equal to 0 amps. I2 is equal to negative 1/2 of an amp. And I3 is equal to negative 2/3 of an amp. So knowing these three mesh currents, how would I find I test?
Negative I3.
Exactly right. So that'll be positive 2/3 of an amp. And then from here, our Thevenin resistance, which is just V test over I test, comes out to be, let's see, so 1 volt divided by 2/3 of an amp is going to look like 3/2 of an ohm. And so we got the exact same result as when we had just used the ratio of our Thevenin voltage to our Norton current. So now let's look at this same thing, but instead of using a test voltage source, we'll use a test current source. So we'll do that down here. So here's my dead network. Across the terminals of my dead network, now I'm going to put a 1 amp current source. I'm choosing direction up and I'm choosing 1 amp, but it literally would not matter if I had chosen direction down or a different number for my current. Here's V test that we're interested in, and here's I test for the network. And by choosing a 1 amp current source, we are effectively saying that I test is exactly equal to 1 amp. And so now we're interested in finding V test. So 1, 2, 3. So I'm going to do nodal analysis here. 1, because I'm trying to solve for a voltage, and 2, because we haven't really done much nodal today, and I want you guys to at least see it more often so that you get comfortable with it. So there's one node. Here's another node. And lastly, I've got this guy right here. Okay. There are no voltage sources, so I don't have any voltage relationship equations or anything like that, or I don't have any voltage sources to take into account for where I choose my ground. So realistically, I could put my ground pretty much anywhere. I'm going to choose the purple node, so the bottommost node as my ground, just because that will let me see it here in a second. So if I find this nodal voltage, VA, that's going to be the same thing as V test. And that's going to make this guy by default VB. So my controlling variable relationship is going to be Vx is equal to negative VB. If anybody needs me to explain why, please say so. Then I'm going to have KCL at node A. So that's going to look like, let's see, negative 0.5 Vx plus VA over 2 ohms plus VA over 6 ohms minus 1 amp is equal to 0. And then I'm going to have KCL at node B. So that's going to look like 0.5 Vx plus VB over 4 ohms is equal to 0. And I'm going to solve this as a 3-equation, 3-unknown system. So in my first equation, my coefficient for VA is 0. My coefficient for VB is going to be positive 1. My coefficient for Vx is going to be positive 1. So I'm just moving everything to the left-hand side of the equal sign. And my constant term is going to look like 0. In my second equation, my coefficient for VA is going to be 1/2 plus 1/6. My coefficient for VB is going to be 0. My coefficient for Vx is going to be negative 1/2. And my constant term is going to be plus 1 amps. And in my third equation, my coefficient for VA is 0. My coefficient for VB is 1/4. And my coefficient for Vx is 1/2. My constant term is 0. And solving that system, I get VA is 3/2 of a volt. VB is 0 volts. And so Vx will wind up being 0 volts as well. And our Thevenin resistance, RTH, is V test over I test. Our test voltage is just the same thing as VA. I mentioned that earlier. So that'll be, 3/2 of a volt divided by 1 amp comes out to be 3/2 of an ohm. And we have gotten the exact same result a third different way. So whenever we have problems like this, where there is a mix of independent and dependent sources, we really have 3 different options for solving for our Thevenin voltage, our Thevenin resistance. We can take the ratio of V Thevenin over I Norton, or we can apply a test voltage source, or we can apply a test current source. And all 3 of those methods will wind up giving us the exact same result. Okay. So for a problem that has both independent and dependent sources, you don't have to use a test source method to find RTH, but you can. If there were a circuit that only had dependent sources, you would have to use the test source method to find RTH. So let's look at your in-class assignment, because I believe I included one of those problems. So if we look at ICA number 11, problem 2, this source right here doesn't have, this circuit right here doesn't have any independent sources at all. So we only can use the test source method to find RTH. So I'm going to draw a source out here to the left. This is going to be V test, and this is going to be I test. And I would like for one of you to tell me if that test source is going to be a voltage source or a current source.
Voltage.
Voltage, okay. And somebody tell me what the value of that voltage source should be.
One volt.
Sure, thank you, Joseph, for carrying the weight of responding to me today. So ultimately here, we're just trying to find that current I test. So I think that mesh analysis would probably be the most appropriate tool to use here. So let's make this mesh current I1 and this mesh current I2. So our controlling variable relationship is going to be Vx is equal to 1.6 kiloohms times I1. And now we just need to write our two KVL equations. So we would have negative 1 volt plus 1.6 kiloohms times I1 plus 8.4 kiloohms times I1 minus I2 is equal to 0. Then we would have 8.4 kiloohms times I2 minus I1 plus 7.5 kiloohms times I2 plus 2Vx is equal to 0. And I'm just going to solve this system as a 3-equation, 3-unknown system. In my first equation, my coefficient for I1 is going to be 1600 ohms. My coefficient for I2 is going to be 0, and my coefficient for Vx is going to be -1. My constant term is going to be 0. In my second equation, my coefficient for I1 is going to be 1600 plus 8400. My coefficient for I2 is going to be -8400. My coefficient for Vx is 0, and my constant term is 1. And in my third equation, my coefficient for I1 is -8400. My coefficient for I2 is +8400 plus 7500. And my coefficient for Vx is 2. My constant term is 0. And solving, I get I1 is going to come out to be 0.138 milliamps. I2 comes out to be 0.045 milliamps, and Vx comes out to be 212 over, 961 volts. We can see that I test is equal to I1. So from here, our Thevenin resistance is 1 volt divided by that 0.138 milliamp. So 1 divided by what's stored in my calculator is X, gives me 7,252.830 ohms, or 7.253 kiloohms, which is indeed the correct answer. For what it's worth, choosing, and I don't think this was particularly difficult, but you guys may disagree. But choosing a test current source here might have actually been a slightly better place to start from, okay? The reason why I say that is if we had chosen, I'm just going to kind of put this in here quickly, a 1 milliamp current source, since Vx is located where it's at, we would know that Vx is just going to come out to be 1.6 volts, and it's no longer an unknown quantity that we have to worry about, right? So in certain cases, one choice of a test voltage source or a test current source will make the problem a little bit easier, but ultimately, in the grand scheme of things, it's going to be solvable either way. Okay, so I don't really have anything else to talk about with you guys today. So if you have any questions, I would be happy to answer them. If not, I hope you enjoy the rest of your Friday afternoon.